So now we want to optimizer, and SGD stands for stochastic gradient descent. So it will be the standard optimizer for these problems. And however, we want to have two different optimizers. So the first optimizer that we want to use is the standard optimizer we created in the other lectures, ANN from scratch, which applies to the dense layer that we have here. So we'll change the weights and the biases from the dense layer. But now we also want to create, based on this, an additional optimizer for the LSTM, because also during the training you might want to have different learning rate schedules for different learnables, ones from the LSTM and ones from the dense layer. However, we still want to maintain the same structure, so we have a method where we just update the parameters when we have a momentum, and as in the previous optimizer, we just look for a particular attribute in the layer. In our case, it's the LSTM. And if there is an attribute which refers to an existing momentum, then it's fine. We just continue with that. But if not, we attach the attribute for to the layer for this particular momentum. And we also know how large this matrix will be because we know the size of the matrix of the learnables from the layer. So we know how large UF is, UI is, and then we attach this attribute, which is the matrix for the momentum. And we do this for all the other learnables, of course. And so this looks like, so we just copy and paste all these different lines and then just modify them accordingly. You can actually do this in a more efficient way. So we can, for example, use the command dirlec directory, which returns a list of all the attributes. And it will, of course, also return all the dunder operators or the dunder operators. But it will also return the other attributes. So we can actually run over such a list and do this in a loop, for example. But I want to show this explicitly, how we would do that. And then, of course, we also need to update the momenta. Also here, I would refer to the lecture ANN from scratch if you want to learn or want to know how momentum works. Roughly speaking, it's taking the landscape of the loss function into account by applying a so-called rolling average, and it reduces the probability to getting trapped in a local minimum. So that's the idea behind momentum. This kind of remembers the structure of the loss function of the previous epochs. And then we calculate these updates based on the momentum, and then we calculate, and then we have these values for the updates, and either we have the momentum, then we calculate it based on the momenta, or if not, then we just apply the normal gradient descent. And we also do this for all the learnables in the LSTM. And then at the end, we change the learnables. And this is what we have done manually in the last chapter, where we were just test running our backpropagation method in the test script. And now the optimizer does it automatically. So we want to use two optimizers, the one optimizer for the dense layer and the other optimizer for the LSTM, and therefore we want to call it optimizer SGD underscore LSTM. So that's the plan. And of course, then we want to test it, and then hopefully it's going to work. So therefore, let me just go to the other screen and just go to our code again. And now I also want to create a new folder for the new chapter. So we just create the new folder that we just call modifying or just optimizer. And then, of course, we also want to navigate to this folder. So let me just do that as well, so that we keep the current code that we have, because we know it works, and can just modify the copy of the code in the other folder. So just in case something goes wrong, that we still have the original. All right, so this is now our LSTM, and we have the forward part, the backward part, we have the dense layer, we have all the activation functions, and what is missing now is the optimizer. So as I said earlier, in principle, we can take a look at the ANN that we have created in the other lectures and just copy and paste the optimizer. And let me just copy and paste the optimizer from the other lectures, which is the optimizer that we just called as so optimizer underscore SGD. Also here, if you haven't watched the other lectures, just feel free to go to the GitHub repository and copy and paste it. So we have these different parameters as the different learning. So we have the learning rate, the decay of the learning rate, and momentum. So this is for the decay of the learning rate. Also here, for the details, I would refer to all the other lectures where I discussed this in more detail. Then if you want to have a momentum, then we have to do this recursively, and therefore we have to check whether there is an attribute attached to the layer, and if not, we're going to do that. And then it changes the updates accordingly, depending on whether we have a momentum or not, and then just performs the actual gradient descent. And then there's also method post update parameters for counting the epochs or iterations, which is needed for updating the learning rate if there's a learning rate decay. And this optimizer works already for the dense layer. So we can just copy and paste that as it is. And it will run for the dense layer. It will not work for our LSTM because for our LSTM, our learnables have, first of all, a different name. So I could, in principle, also rename them as weights if you wish. We could also just save those matrices in one particular matrix altogether and change it all together. So then the code would be, of course, more compact. So this would be an option, of course. But also here, I want to keep it simple, even though if the code is then less compact, that you see really what the code actually does. So what we have to do now is that we create a new optimizer, and we just call this optimizer optimizer SGD underscore LSTM. So we can actually copy and paste everything but the momentum part. So let me just copy and paste all of it and then remove the momentum part, because we still need the learning rate and the decay and momentum as an input. But let me just rename this as optimizer LSTM. We want to have properly learning rate decay, so that's the same thing, and also need to change the iterations. What is different now is this part here. So if we want to add a momentum, then we first have to check for the particular attribute. And we can do this with has attribute. By the way, I just want to show you also how this command dir works. So for example, when we have our LSTM, and it gives us or returns a list of all the attributes, but you all have the dunder operators as well. But you can exclude them, of course, by looking for the double underscore. But you have all these learnables here. And if you name them accordingly, then it's pretty easy actually to extract those learnables or attach those attributes in the loop. So you can also do this, of course, using comprehension. I still want to do this explicitly, as I said. So if there is no attribute for the momentum, we have to look for a keyword. And the keyword is related to one of those learnables. So let's take UF, for example. So if the layer does not have UF underscore momentum, it doesn't have any attribute for any momentum at all. and then it will attach these attributes accordingly. So you can also use any other keyword which refers to a learnable. So it could be also WF, WI momentum. But the key point is that we now attach the attributes for the momentum. And this is just a very technical part. So it's just copy and paste essentially. And so we want to do this, and that's why I do it this way. So we just go to optimizer SGD underscore LSTM. And then we have to do this for all the learnables. So it will see the different learnables here. Then it knows how large they are, what the shape is, so we can set up the momentum. And then we just do this for all the other learnables. So it's the exact same thing. And also here, I want to shorten this a bit. That's the same. We just correct this. So here I want to shorten this a bit by just copy and pasting that. So this is really a very technical part. However, make sure that it's always the same learnable refers to, even though it's just creating or pre-allocating space, you will get an error message if it's not the correct one. For example, if you use a bias for a matrix or something like that. But still, please keep track of the correct names. So then, if there's no momentum, although we want to have one, the attributes will be attached, and then we have the first step in the recursive way to calculate momentum. So we also need to calculate these updates now. And also here, this is a very technical part. So we just do this for all the learnables. So the only thing you have to do now, even if you don't know how it actually works, is using this optimizer and just using the variable names of the learnables. So also here, I just want to shorten that and copy and paste that. So instead of having bias updates, you have UF updates, UF momentum, and so on. But here really, again, make sure that it's always the correct variables you're referring to. And we also do this for the biases. And if there's no momentum, we just calculate those updates just according to the standard gradient descent method. So we also have to change that. So you see, if you compare this to the optimizer we have for the dense layer, it's exactly the same structure. The only thing that changes is the name of the learnables, the variable names, but it's the exact same structure. So that's lots of code. Looks a bit lengthy. But again, in principle, you can run a comprehension loop using the command dir, like the one I showed you here. So then we have our optimizer, and now we can test our optimizer. So let's do that, and let's test our optimizer. So let me just call our LSTM again. Here, this will be the same. So we can just rerun this part. Now we have the optimizer, and now we just set up the different optimizers. So we start with the optimizer LSTM. Which is the optimizer LSTM. And let's start with the default values The only difference is that we have, so with the default values where we have zero momentum, no decay, but let's also have a learning rate which is relatively small. So let me just also do that. So of course then we have to rerun it. And we also want to start with a learning rate for the dense layers, which is also relatively small. So maybe you should also change the default settings here as well. So we just call two optimizers, one for the LSTM and one for the dense layer. And of course, please, you can experiment with different learning rates, different decays, different momenta. So we're not going to need this anymore. We still need the forward part. We still need the same backward part, but what we don't need is this here. So we don't need to reset those values manually anymore, because that's what's going to be done now in the optimizer. So what do we have to do now? So we have to now apply those optimizers. So first of all, we start with optimizer LSTM, and we start with the pre-updated parameters. What was it for? It is for calculating the current learning rate if there's a learning rate decay. In our case, no, we haven't started with a learning rate decay. So because we use the default values, there's no learning rate decay. But just in case if there's a learning rate decay, we have this part already being called, and it will just perform the learning rate decay. And we also want to do the same thing for the dense layer, because you also might have added a learning rate decay. And then we continue with the actual updating of the parameters. So we just call different optimizers and the corresponding methods. So we just call optimizer update parameter, and then we take, and the input is the layer. So we do this with the dense layer, with the first dense layer. And also we have to update a parameter in the second dense layer. And then in those layers, it's looking for the different attributes and changes the learnables. So it looks for layer the weights and layer the biases and change them accordingly. And in the same way, we want to do this for the optimizer LSTM. And here it looks for the attributes layer dot, for example, let's take this one, DUF, DWF, DWI. So it looks for all these different attributes and change them, changes the attributes accordingly. So we have to do the same thing for the LSTM. And we do this with the optimizer LSTM. And the layer then is just the LSTM. So that updates all the parameters, and now we just have to update all the, so we have to run all the post update parameters. That was for counting the iterations, which we will need if we have a learning rate decay. So we have to do that as well. Otherwise, it would not really count them correctly. So we do this with the LSTM. And we also do this with the dense layer. So we just copy and paste this part here. And here we go. So let me just show code so far. So the forward part doesn't change. What changed is calling the optimizers. Then forward part is still the same. The backward part also doesn't change. The only thing that changes is this part where we pre-updated parameters, then updated parameters, and post updated parameters. So let's test run it. So let me just remove those plots. Again, I want to rerun and compiling the LSTM. And now I want to test run our script, and let's see what it changes. So the optimizer just optimizes the learnables automatically. So what we did manually before happens now automatically. And so nothing should actually change. Of course, we always start with randomly set values. So the absolute values themselves, they of course will be different, but the overall scheme will not change. And that's what you should also see if you run the code yourself. So the loss should go down with the epochs, and it should do it kind of smoothly. So let me just wait until it's done. So the code finished, and you see it's again a very nice and smooth curve, and we roughly ended up with the same value for the loss after 100 epochs. So therefore, let me just summarize again what we have modified. So we used an optimizer that we have created already in the previous lectures. Again, I would refer to those lectures if you want to know about the details. For this particular lecture now, it's sufficient to copy and paste it from the GitHub repository. And we want to use two optimizers, one for the dense layer and one for the actual LSTM, because we want to keep it separately. And we just maintain the same structure. We only change the variable names accordingly. So that's the only difference. And then we run it in our script just to test it, and with a small learning rate, of course. And therefore, everything that we did manually in the previous chapter is being done now by our optimizer. So we run the different methods for pre-updating the parameters for both optimizer in case we have learning rate decay. And those values can be different, of course. So for every optimizer, we can have a different learning rate decay, which actually makes sense if you want to optimize the training. Then we apply the optimizer to the dense layer and to the LSTM. And then we also run the post-update parameter methods for both optimizer for counting the iterations, which we need for the learning rate decay, if there is any. And then we rerun our code, and it should produce more or less the same result. And now the optimization process is fully automated. Again, I want to stress that this is not the way how you really do this if you write a package. So you would write the code of the optimizer in a more compact form using the command dir and running over a comprehension loop, for example. All right, so now everything works. So therefore we can just put it into a package, and then we can of course run the package. So we want to run the training then thoroughly for many epochs, for different training parameters. And of course, finally, we want to apply our LSTM to a new data set, to new data, and want to compare the performance of the LSTM to the classical RNN that we have created earlier, and we'll see the difference.